after, because that's what the experimentalists are doing. So here's the whole thing summed up. Real world R3, 3D vectors, U2 world, complex 2D vectors, and all done with these devices, which we're gonna get serious about that device, because it does sort of marry these two spaces into one. Any questions about what you have so far? It's a hell of a lot of stuff. But it's compressible. That's what's cool about it. If you play with it a little bit, give you a couple of problems to do on this, you become familiar with it. And then there are a lot of seminars that you can go to and actually understand what they're doing better than they understand it. Because I've shown this to a lot of people that have worked with various pieces of Stokes stuff, and they said, wow, that's kind of neat. And then, of course, Dudley Hirschfeld has a Nobel Prize. He's still fascinated with this thing. As is Michael Berry. Michael Berry's famous guy with Berry phase. He was blown away when he saw that at Georgia Tech.
Actually, I was going to mention that that's what one of the things Dr. Singh was looking at is when you change polarization state from like in a cyclic way, and then you can measure the overall phase by the solid angle on that thing.
That's a way of one of the ways the Berry phase occurs, and you can. I have a problem where you simply crank the thing first this way, and then a certain angle, and crank it again, and you make a path up here, and then you return whatever the shortest distance is. You will see that the area that's enclosed by the spin vector.
Actually, that's exactly what we can do with the quarter wave, half wave, quarter wave plate combination. But I don't. I mean,
right.
This is don't like.
That's right.
Seeing
that's right.
more deeper mathematics for me is more neat or something.
This one right here. This one is one that this is a Faraday effect right here. But what you're talking about is a rotation from, say, X polarization through the C here, which is right circular, all the way down to Y. So quarter wave plate gets you to here. A half wave plate takes you halfway. And then if you want to do it, any more, you just put more and more plates up to the point where you don't absorb. I mean, finally, they each have a little noise and absorption things, so you can't do it forever because the signal goes down. But yeah, that's...
One question that I had was, is it possible to take these states and put it on like a different shape besides a sphere? Is it even possible, or does that question make sense?
Wait a minute. I got part of your question.
It's a good question.
On this
Repeat
one,
it more
every single point has some kind of ellipse or circle or whatever,
right.
In some particular state.
That's right.
Is it possible to use different shapes besides this one, and can that thing morph into other...
What's not really shown by it is the fact that there are two spheres there. And let me exhibit that. And we'll see this in more detail on Thursday, because we're going to address those issues of double value. But look what's going on here. Here comes X polarization, okay? I've colored one of those arrows dark red, or bright red, I should say, and the other one sort of brown, right? And then I'm working my way down, okay, until I'm here, okay? You can see the red guy has only rotated, you see, from X to Y, right? And then he's going to keep doing that, you see. He came here. He's going to, go through. He's not going to go through that point. He's going to go behind the scenes here through that guy, and then come back. And you see what he's going to do is he's going to he's come down this way, and he's now this way. He's going to work his way back and back and back. Now he's kind of hidden in there, and then he's going to end up here, right? We've already seen this. Remember when I showed you the minus occurring on a finish of a Lissajous pattern? It looked like the Lissajous was done, right? But you were stuck over in the other half of the world, right? So he's got to go again around in order to get back. So that there are really two spheres, the spheres on which he went on the outgoing voyage, and then on the next part of returning, he's going on a second sphere. So that's the double covering.
Is it the same reason going from the U2 to the R3?
Exactly that. Yeah. Yeah, exactly. Yeah. It's double valued. Just like the complex variables is plus and minus square root, right? Same number, one's got a minus sign of the other. So it isn't too different from the double valuedness of just the square root. But that's what we did to the Hamiltonian, right?
So that's why there's like, with the geometric phase, I forget what that was, like there's a
well, there's the dynamic
solid
phase.
angle that you actually get to the Hamilton, or is it the energy, I think? There's a factor of 2
Right.
in the Berry's phase.
And the thing that you have to subtract out of it is the dynamic phase that would just come because this thing is turning. And that's where it's sometimes hard to see the Berry phase angle, since it's part of something that's doing this, but you think of it, here's a dynamic phase. If I'd taken that out, it would have gone, that far, and that would be the Berry angle. That doesn't explain very well, but the idea of locating something that has to do with the geometry, right, as opposed to the thing that simply has to do with the fact that you're doing exponential of something times time. Yeah, we'll explore the issues, at least some of the issues of that, just using this device and a couple of simple equations.
And I think I just had one other question. I'm not sure if I understood the rotation on the X or the X or the Y axis.
Let's go back.
Only the first one, rotations.
Was it those blue vectors?
Before it turned into that gray cone and the yellow ball, there was one more.
You're talking about this.
One more before that.
One more before that.
It was when we rotated with R and then minus R on one of the polyspin. I mean, one of the sigma matrices.
I think you were composing.
There.
And it split into a sigma X and a sigma.
You were transforming.
Transforming.
Yeah, you transformed the sigma A.
I've got to go back a little further than this. Is this what you're?
Yeah. I'm not exactly. I can't see like which ones are rotating in there. I think you said that they're.
Oh, okay, let's go slowly through that. Basically, this one is sort of showing what we're going to do. Is we're going to start with this vector right here, right on the Z or A axis. And if I do that, this vector right here is going to swing up and be on the B or X axis. So this is X, that's Z. Y is the axis that we're going to actually have the crank on. This axis right here is just a general one, right? That's the general possibility. I can have my crank anywhere. But this one's taking the very special case of using the C axis crank, the Y matrix. And that starts right here. Here's I come in from this side to operate on whatever is here, but I'm really coming in from both sides because this operator can't, you can't finish the operation just with one of these things, and that's where the 2 to 1 really comes algebraically. So what I'm doing is I'm applying this matrix, that's this one, that's this crank, right?
I think I understand. It's just rotating it by the beta from the original axis.
Yes.
And then
yes.
You said that it breaks up into the A component and a B component, and that's why there were two sigmas later on.
Well, when you do the algebra here, you see, you find that the result of rotating the A is a combination of A and B.
But if you wrote out what R and then R minus is in terms of the sigmas already in the first place, you still get that combination?
What that is, because it's got a 2 in it, what that is, that angle is an alpha or beta, an Euler angle. It's an angle from the 3D space. Remember, things go twice as fast in the 3D space. The spinor space is half-assed, right? Half-fast. Okay? So I need yet another equation for this one. I don't need another equation for C, because C is not going to move. It's on the axis of rotation, which is the green vector there. That's the crank vector that we're using, is on the C-axis. And it's turning all of the operators that aren't on the C-axis by a certain angle. That angle is twice the angle of rotation that the spinner would experience. This thing, you know what's going to happen if I put this on a little x, y of a spinner. It's just going to rotate this thing by angle theta
So
c.
in the picture, would that phi vector axis, would that have to also rotate with the other rotated, does it make sense that the...
Well, what we've got so far is just what's happened to this vector, sigma A. We still have to do its orthogonal complement, right? And that involves, see if I've got it here. Yeah, there. I still have to do the same rotation if I'm going to describe what's going on in this plane. I've got to apply it to this too, right? I finished taking A over to here and getting its components. Its Z component, right, which is the A component, is cosine, right?
Oh, no, I understand that. So the other one is also needing to rotate.
Yeah, to completely describe what happens in the AB plane.
That coordinate system,
Yes.
the original sigma.
And so this is just another one of those matrices that looks like this. When you take this component, cosine 2 phi, sine 2 phi, that would be corresponding to cosine phi and sine phi in spinor world, right? But this is 2 phi. And then the other column is these two numbers here, minus sine and cosine, right? And that would be taking care of A and B together. This is what happens to the A. It goes dong. While that's happening, B is going down. That's what this minus sign is relative to the A axis.
And C is unchanged.
So you really have to just realize that all of this complicated stuff here is doing nothing but that.
That makes sense. I just was trying to place where the phi vector or phi vector also, did that also rotate with
the
those?
phi vector.
The projections weren't
Yeah, the phi
obvious.
vector is your crank. Okay? The phi vector, which later becomes the omega, right? It has an angular velocity of omega, lowercase in a spinor, uppercase in the three-dimensional space. That vector is this guy right here. That's the crank. And that is this operator's crank. If that operator is going to be cranking, that's where the crank is, in the three-dimensional space. Does that make sense?
So you're forcing the phi vector to go along the C direction to crank the other
Yeah,
two.
this maybe is a little misleading, because I was just trying to show that a crank, you know, of an operator, that's this vector right here, okay, could be anywhere,
Okay.
right?
If we
I should
use-
probably have erased
If we use projection lines, if we
because
trued it up.
what
it would
I've
be-
done, what I've done is I don't want the thing way out there. I can't figure out what. There's so many cosines and sines, right? So let's do this one,
Okay.
right? That's what this is all about.
That
It's
makes,
just that.
yeah, that makes sense.
Does that make sense?
Yes, it does.
Yeah. Good question.
But
I
you
mean,
could, like he was,
You gotta
were
split this
saying-
open.
about to say is that the phi could be split along those directions. You could see how those would rotate. So you could change the lengths of the orange, the red, and the green as well.
It's
Yep.
in essence what he's done halfway
Yeah.
already. He's already taken two of the bases and transformed them.
Yeah.
If we knew exactly how the other two bases vector or
Yeah,
bases
no,
transformed.
I see.
You
You could play the
Maybe you
game
could
where
change length
you
as
use
they rotate.
you use B, all right, to move C and A, and it would be the same story with different, slightly different components. And we would name them differently too, because this one is being named after C. If I was going to use that operator to move these two guys. And the idea, of course, is an operator doesn't move itself. And the reason that is because if I use an A operator here and here, A and A inverse, right? Well, this A commutes with them, right? So the inverse cancels, the A inverse cancels the A, goes right through this thing, does nothing, it leaves the sigma A alone.
Three quarters of the way down.
Yeah. So the operator never can rotate itself.
It's metaphysical.
Except that it can rotate its phase. Right, that's the gamma. That's why this is so important, to have that gamma hanging off of there.
So that blue arrow is the...
Just general case axis. Yeah, general, one of these things. That's, you remember what we're doing here is we're generalizing something that happens in 2 dimensions to 3. So this is represented by this crazy thing here, and there's some time stuff there if you want to put it there, but that's what we're really looking at, is this sigma phi operator, which is that thing, represented by that thing.
And that's
Right.
just totally generic, not describing the rotation that's going on.
That's generic, yeah, the blue stuff is generic. And general. I guess general and generic is kind of a synonymic.
So then in the next, I don't know if I'm taking too much time, but the next
Oh,
one
no.
where you show like almost the same picture but with the column and it traces out
Yes.
that. So the
Yes.
center of that is the crank, or that would be the phi.
You'll see it again, Paul.
I forget whether
the
we went
omega, I
forward
think,
to that
is
or backwards. I think we did.
Forward.
Let's go forwards.
So,
This.
I got a question. So these...
Well, let me finish this first. Here's the crank.
Coming dead
Now
center
it's
of
been
the-
named by the uppercase omega, not the lowercase omega that goes with the phi. Okay, this is named with a, to indicate that this is in our space, and we go fast in our space. We're not half fast. Okay, so there's the omega. It's just sitting there, and it's cranking the spin vector around like
I see.
that.
Okay, so S is like a physical given state, and then we use the crank, which is some combination of the A, B, and C to
That's
make
right.
it dynamically move.
And it makes the Hamiltonian.
Okay.
It makes the evolution operator, right? Which, oh my God,
By definition.
I disobeyed the law of Arkansas. It makes the U operator, e to the Hamiltonian with the i's and the omega and h bars and all that. E to that Hamiltonian is the U operator, time evolution operator, and that's general, right? All the way through relativistic quantum mechanics. That's a general equation. It can be matrices that are infinite by infinite, but it's a very general thing. We're looking at the simplest case, 2 dimensions. Simplest non-trivial case. I mean, there's a 1 dimension too. That's just phase. That's just a phasor. Which is where this came from, right? E to the minus I omega t.
Oh, and it's not a question, but I just want to let you know that I don't know if I'll be able to finish the homework assigned by this Thursday because I have an annual review coming up.
No deadlines in here. Yes,
But
do it.
I will. I don't want to get behind. So
Yeah, but that's right. You want to make sure that you understand the nitty-gritty details.
We give a heads up. And Professor Harter
Yeah.
always works.
I mean, with a small class like this, of course, you can get nitty-gritty details as we go along, but it's much better to, find them yourself, because then it's more. It goes closer to permanent core memory instead of just sitting in something that
Short
gets
term.
flushed.
Yeah.
Yeah.
Let me sweep by you here and get this. I guess I'll do some trimming.